In this problem, we'll take up example related to the angle struts over here. So we'll see how we can analyze a double angle strut. So this is the section what we have. A double angle discontinuous strut ISA 70 by 70 by 8 of length 3 meter. The two angles are placed back to back. So this is what is shown here. This is the arrangement over here. So they have been placed back to back over here. So the length of this member is 3 meter. Angle section 70 by 70 by 8. This is what is the member details given to us. So in this case, you have to determine the design compressive strength. If the first case is the angles are placed on the opposite side of a gusset plate, and in the second case, the angles are placed on the same side of the gusset plate. In both the cases, angles have been positioned back to back. But thing is, whether they will be on the opposite faces of the gusset plate or they'll be on the same face of the gusset plate. Based on that, you will have to determine what is the design strength for that member. So thickness of gusset plate is given as 10 mm. Let us start with the first case here. And before that, we require the properties of ISA 70 by 70 by 8. So the properties we can take it from the steel table. And in this case, we have the property of this single angle ISA 70 by 70 by 8. Cross sectional area is 1060 mm square. Moment of inertia about y-axis 47.4 into 10 raised to 4 mm raised to 4. This will be same even about the z-axis because this is a equal angle section. And the radius of gyration is 21.2 mm rz as well as ry. And cy is the distance of centroid of the angle section. Okay, so cy and cz, they will be 20.2 mm. I have written one of the property of this section. For an equal angle section, they will be same about the other axis also here. In case if it is unequal angle section, then they will be differing. Now first case, angles are placed on the opposite side of the gusset plate. This is the arrangement. This is the gusset plate what has been provided. The two angles have been placed on the opposite side of this gusset plate. Okay, so for this, what will be the load carrying capacity of this member? First is we need to find out what is the radius of gyration of this compound section for this arrangement when angles are placed on the opposite side of the gusset plate. So we need to find radius of gyration about z-axis and about y-axis, and out of these two, whichever will be the least radius of gyration, that will be taken for calculation of the load carrying capacity. So what we have is, we know what is the moment of inertia of this angle section about these its own centroidal axis. It is here we have taken out from the steel table 47.4 into 10 raised to 4. Now we have to determine the moment of inertia about this y-axis of the entire section passing through the centroid of this entire compound section over here, and also check it with the moment of inertia about the z-axis. Okay, so for moment of inertia about this vertical axis y-axis, we need to apply the parallel axis theorem here. Since there are two angle sections, we'll determine the moment of inertia of one of the angle about this vertical axis, then just multiply that by 2 to get the moment of inertia of this entire compound section. Okay, so if I use this equation, so 2 for the two angle sections, IYY or plus A into YC square. It is like IGG plus A into YC square. Moment of inertia about its own centroidal axis plus the area of the section multiplied by the square of the distance between the two centroids, between the two axes, its centroidal axis and the axis about which we are calculating the moment of inertia. So this is what the parallel axis theorem is. So in this case, 47.4 into 10 raised to 4 mi of the angle section, single angle section, plus area 1060 mm square, plus distance will be cy plus half the thickness of gusset plate. So cy 20.2 plus 10 by 2 thickness of gusset plate and square of this entire distance. And here the area of gusset plate will not be considered. Anywhere we are not taking the contribution of gusset plate towards the moment of inertia, because these gusset plates are only present at the end connections. The gusset plates will not run throughout the length of the member. So buckling is mainly critical at the middle of the member. That is a point where buckling will take place, or the properties of the section will be minimum. We don't have any gusset plate being provided in between the length. So for that purpose, that thickness of the gusset plate or the area of gusset plate and its contribution towards the moment of inertia has been neglected here. So on doing this calculation, we'll get to know that the moment of inertia of the entire section, this double angle section about this vertical y-axis, will be 229.42 into 10 raised to 4 mm raised to 4. So this is moment of inertia about one of the axis. Now what will be the radius of gyration about that y-axis? So I by a, root of I by a, that is 229.42 into 10 raised to 4 divided by, since we are considering two angle section, 2 into 1060, 2 into area of one section. So if you take this, that will tell us that the radius of gyration about y-axis ry is 32.90 mm. Okay. Now radius of gyration about z-axis, about this horizontal axis, will be same as this rz itself. Because now if you take this centroidal axis, z-axis, so when you combine the two sections together in this form, their CG and the CG of entire section will be coinciding. They will be lying in the same on the same line. So this parallel axis theorem will be just it will be 2 into Iz, twice the moment of inertia of the individual section about z axis. That is the moment of inertia of the double angle section about z axis. So here when you calculate the radius of gyration, what happens is Iz of the double angle section divided by the total area, that is 2 into Iz divided by 2 into A. It is nothing but Iz by A. That will again give back the Rz value, which will be there for the single angle section, which is 21.2 mm. So if you compare these two, Ry as well as Rz, it tells us that the least radius of gyration or the minimum radius of gyration is 21.2 mm. Okay, so this 21.2 mm, this radius of gyration has to be considered while calculating the strength of the section or the strength of the member in compression. Now what will be the effective length? So in the clause we have seen that the effective length in case of a double angle section, that is in this clause 7.5.2.1, page 48 of IS 800/2007, the effective length in case of a double angle section, it will be varying from 0.7 to 0.85 times the unsupported length. So depending on fixity, what amount of fixity we have at the end connections, based on that we will have to choose the value of this K, which varies from 0.7 to 0.85. So in case if you have so here it is assumed that the ends are hinged. Okay, so ends have been assumed as hinged. For that purpose I have gone for taking a value of 0.85. Okay, so K value will be 0.85. So as the fixity increases at the ends, so this value will go on reducing. Okay, so it will be 0.7 for completely fixed end. In this, it is assumed that the ends have been hinged, so the K value is 0.85 over here. So with that, the slenderness ratio KL by R minimum, that is 0.85 into 3000 divided by 21.2, it comes out as 120.28 over here. Now we can use the tables from the IS 800. The first thing what we need to know is what is the buckling class. So in this table 10 of page 44, we get to know what is the buckling class for the angle section. So for angle sections it remains C, buckling class will remain C. Later further, what if we refer to table 9C, which gives us FCD value for depending on KL by R and the yield strength, we'll come to know that FCD is 83.44 Newton per mm square for this section, and design compressive strength of the member will be PD, which is AE into FCD. So AE will be 2 into 1060, 2 into area of each angle section, FCD we got it as 83.44. So PD comes out as 176.89 kilonewton. So this is for first case when we uh, had the two angle section being placed on the opposite side of the gusset plate. For this we went for calculating what is the radius of gyration of about this y-axis. Okay, so by applying the parallel axis theorem, and we also calculated the radius of gyration about the z-axis. Okay, in this case the centroidal z-axis of this entire section, compound section, will coincide with the centroids of the individual angles. So radius of gyration Rz will be simply Iz by A. Okay, knowing this too, we came to conclusion that the minimum radius of gyration is are about z-axis. On that basis, we went for determining the slenderness ratio. Refer table number 9C, okay, for buckling class C, and there we got FCD value. Okay, then the load carrying capacity can be determined knowing the area of the section and FCD value here. So that was first case. Now coming to second case, what is there in second case is the two angle sections. Okay, they have been placed back to back here like this, but they have been provided on the same side of the gusset plate. This is the gusset plate. Now they have been placed on the same side of the gusset plate, not on the opposite side. On the same face of the gusset plate, the two angles have been positioned over here. So in this case, what happens is, what will be the radius of gyration now? In this, what will be the radius of gyration about this y-axis as well as about the z-axis? Okay, so about y-axis it will remain the same. That will be 21.2. Okay, that will be same as that of the single angle section. Okay, because this radius of gyration will be 2 times the I of individual section divided by 2 into A. Okay, so that will be the right. So this Ry is given by 2 into Iyy divided by 2 into A. Okay, when I position them like this CG of this entire section will pass through the CG of these two angles. Okay, so Ry will be two angle sections are involved here. So 2 into Iy, total moment of inertia about y-axis will be 2 into moment of inertia of individual angle section about this its own central axis. Okay, total area is 2 into area of this each angle section. So this will be the radius of gyration about y-axis. That is nothing but it will give you back Iyy divided by A, root of Iyy divided by A. That is the radius of gyration of one ISA 70 by 70 by 8. Okay, so that will be 21.2 mm. Now if we want to check what will be the moment of inertia about this z axis, okay, so Izz will be obtained from applying parallel axis theorem. So in this case, moment of inertia of the individual angle section, okay, plus A into yc square. So yc here will be simply cyy, okay, cyy in this direction. Okay, so centroidal axis, distance of centroid of this angle section from z axis, that is nothing but cyy, that is 20.2. So this will be the Iz value of both the angles about z axis, 90.952 into 10 raised to 4 mm raised to 4. From this, Rz comes out to be 29.24 mm. Okay, so if I compare Ry and Rz, we find that Ry is having the least value. So our minimum radius of gyration is Ry, which is 21.2 mm. Based on this, KL by R will again turn out as 120.28, which was there in the earlier case. So same. Now on that basis, again if we go and refer table 9C, FCD, and if we calculate the load carrying capacity of the section, it comes out to be 176.89. There is no change in the load carrying capacity in this particular case, whether they are placed on the opposite side or on the same face of the gusset plate over here. Okay, so you need to determine what is the radius of gyration about the two axes of the compound section. Out of those two, which is least, that has to be taken in the calculation. Okay, so sometimes it requires the application of parallel axis theorem. Okay, like we had in this case about z axis, whereas about y axis what is happening is when I place them back to back, the CG of both the angle section will be passing through the same line. So this line itself will be the centroidal axis of this compound section here. Okay, So this will be the calculation for double angle sections. This is how we need to proceed for double angle section. Double angle section are considered to be loaded through both the legs. For that purpose, the effective length what we consider will be from 0.7 to 0.85 times the unsupported length, or 0.7 to 0.85 times the distance between the centers of the connection. That is the effective length calculation what you come across in double angle sections. Okay, you don't have to go for calculating any equivalent slenderness ratio lambda e. That is only in case of single angle sections. Here it will be considered that both angle sections are loaded through both the legs. So we will be taking k value, effective length factor, from 0.7 to 0.85. If it is completely fixed, adopt a k value of 0.7. If it is completely hinged, adopt a value of 0.85, or else for any partial fixity you can go for a value between 0.7 to 0.85, and on that basis determine what is the slenderness ratio KL by R. And you can proceed either using equations, that is for by calculating phi and the stress reduction factor, and then finding FCD. That can also be done here. In that case, alpha will be 0.49, value of alpha in that equation, buckling class C. It will be always buckling class C for angle sections. So alpha will be 0.49. Then from that you need to obtain phi and find FCD. Okay, or else you can go ahead with getting the stress reduction factors chi from table 8C, and alternatively we can use table 9C, what we have done in this example over here. That is, you can find FCD directly by using table 9C.